Alright, one last example, and hopefully this will be enough for you to get started on your assignment and roughly know what to do. So the question is again the same. I want to find the power series representation for this function, x cubed over 2 minus x, and the 2 minus x is squared. So I'm going to start off by writing this as x cubed over 2 minus x squared, and this is the same thing as x cubed times 1 over 2 minus x squared. And the goal here is going to be, I find a power series for 1 over 2 minus x squared, and then I'll just multiply x cubed in later. And of course, the ever so useful power series is this one, equal to the sum of n equals 0 to infinity of x to the n. And this is valid for x between -1 and 1. So, remember how last time we had a function, we took its derivative, found the power series, and then integrated back to get the original function. That's a lot of words, but we're going to do sort of almost the same thing here. We're going to take a look at 1 over 2 minus x squared. Right, and the closest thing this looks like is, well, 1 over 2 minus x. And in fact, I know that if I take the derivative of 1 over 2 minus x, somehow it's going to become squared on the bottom. Right, here, I'll just show you. We've got 2 minus x to the -1, right? I take the derivative, the -1 comes down, and up comes the -2, right? -2, so it's going to be something squared on the bottom. So I don't know exactly what that is, and heck, let's find out. So d by dx of 2 minus x to the -1, well, that's just equal to -2 minus x to the -2, but of course chain rule tells me I need a -1. -1 and the negative cancel, and I'm left with, wow, it's exactly what I want. This wasn't planned at all. Alright, so here's the picture so far. I have a function which is relatively easy to cram it into this type of form, right? I can take 1 over 2 minus x, and I'll show you in just a minute how we can get this into this type of form. And if I take the derivative, I get something that's really useful for me in order to get the power series of what I eventually want. So let's see what we're going to get. I take 1 over 2 minus x. Right, 1 over 2 minus x, and I want to get it into the form in up here. So the 2 is not a 1, so I factor out the 2, like this. 1 over 1 minus, and of course everything in math has to work out, this becomes x over 2. Hey, what do you know? 1 over 1 minus x over 2 is in the form of 1 over 1 minus x, except x is just now x over 2. So this is equal to 1/2 times the sum of n equals 0 to infinity of x over 2 to the n. That x looks really funny. All right, so the restriction is, of course, x over 2 has to be less than 1. Or in other words, the absolute value of x has to be less than 2. All right, so continuing, we found a power series representation for 1 over 2 minus x. Well, it's this right here. So if I take the derivative of both sides, I'll then have a power series representation for 1 over 2 minus x squared. So I take the derivative of both sides. 1 over 2 minus x. And I'm just going to write this out as taking the derivative of half times 1 plus x over 2 plus x over 2 squared plus x over 2 cubed, and this goes on forever. And this is actually a point that I didn't cover too much in class, but I will again on Wednesday. But of course, it'd be helpful for you to have that now because you might want to start your assignment before the day it's due. So we've got 1 plus x over 2 plus these things all the way to infinity. And if I take the derivative, well, the left-hand side, I've already done this, so I know. Whoops. And this is 1 over 2 minus x squared. And this is equal to, well, the half I can pull out, and this would give me the derivative of 1 is just 0, plus 1/2 plus 2x over 4 plus 3x squared over 8, and this just kind of continues on forever. So notice what happened here. With the n equals 0 term, the 1 became a 0. For the n equals 1 term, x over 2 became 1/2. Well, this one's x squared over 4, right? So I left the 1 over 4, and then the derivative of x squared is just 2x. And same thing over here, 3x squared is the derivative of x cubed, and it's all over 8, because that's the constant. Sorry if it looks like I jumped a step there, but it is the derivative if you take the derivative. So, comparing this to our original function, so remember, one thing we can always do is we can work with the sum itself. Right, so if I take the derivative of my sum, and this is the derivative, n equals 0 to infinity, and I'm just going to write x to the n over 2 to the n. Right, that's just expanding the x to the n over 2 to the n. So here I've got, this is equal to half, and the 2 to the n is just a constant, so I can just leave it, and the derivative of x to the n, well, that's just n x to the n minus 1, right? Power rule, something you should have learned last term. All right. Right, subtract 1 from the top and multiply it by the previous exponent, so n. All right, so what you're going to notice here is the n equals 0 term is actually very confusing and doesn't work out nicely. Right, so this is equal to 1/2, and the n equals 0 term, well, this is 0 times x to the negative 1 over 2 to the n. Right, sorry, 2 to the 0, I guess, if I'm plugging in. Here, this is n equals 0, and then I have the rest of the series. So the series just looks like n equals 1 to infinity n x n minus 1. It's the exact same thing as before. So you might actually get kind of confused. This is like 0 over x, but sometimes x can be chosen to be 0. So this term is rather problematic. But if we actually expanded our term over here, you can see what happens, right? The 1, or whatever this number is, because it's always going to start off at a number, this number, when you take the derivative, just becomes 0. So even though the sum notation is a little bit confusing, we can just make this term 0. And in fact it is, right? We expanded the sum, took the derivative of 1, and it's 0. So in fact, whenever we have take a derivative for a power series, we can just start off the sum at 1. So this here is equal to 1/2 times the sum of n equals 1 to infinity n x to the n minus 1 over 2 to the n. So notice how I started at 1 and not at 0. And the intuition you can think of it as is if it started from 0, you would have the n here, and it'd be 0 times whatever. So there you have it. This is the power series representation of 1 over 2 minus x squared. Right? But the original one we wanted was x cubed times 1 over 2 minus x squared. Right? So of course x cubed times 1/2 times the sum from 1 to infinity of n x to the n minus 1 over 2 to the n. These two would be the same thing, right? Because we just found the power series representation for 1 over 2 minus x squared, and that's this right here. Right, so how do I move this in? Well, I can bring the x cubed inside the sum, right? X cubed does not depend on n, and so this would be 1/2 times n equals 1 to infinity of n x to the 3 times x to the n minus 1. Well, it's x to the n minus 1 plus 3. Right? I'm just adding the exponents over 2n, and this is just going to be equal to the sum, and I'm bringing the 2 in as well. Why not? And this is n x to the n plus 2. Right? Negative 1 plus 3 is 2 over 2 to the n plus 1. And I guess if you really want to be precise and, well, not so much precise, but just I guess follow convention and start your series at n equals 0, well, you can. And you can just say this is equal to the sum of n equals 0 to infinity and just shift the index. Right? So we start at 1 here, so then we would need n plus 1 here. Right? N plus 1 starting from 0 is the same thing as n starting from 1. Right? If I plug in 3 here, I would get 4. And in this sum, this would correspond to 4, and I would get 4 here. So that all works out. So x to the n plus 3, because the first term is in fact x cubed, and same up here. And on the bottom, we'd have 2 to the n plus 2, I believe. Yes, that's right. So if I plugged in 0 here, I'd have 2 to the 2. If I plugged in 1, I'd have 2 to the 2 again. So there you have it. This is a power series representation of the original function that we had. So of course, if you actually just want to leave it like this on the second last line, that's totally fine. They're both legitimately accurate. So just a quick recap. What did we do? We took a function that we want to find a power series representation for, x cubed over 2 minus x, and the 2 minus x is squared. So we saw that 1 over 2 minus x squared looks a lot like 1 over 2 minus x. And we know, in fact, if we take the derivative of this, then we get back something very similar. In fact, it's the same as what we actually are looking for. So we take the 1 over 2 minus x and then rewrite it in a form where we can make use of our original power series up here, right? So 1 over 1 minus x over 2 is the same as 1 over 1 minus x, except, well, the x part is different. So I can follow the formula, plug this in, and then what I can do is I can take the derivative of both sides, end back up with the one that I was looking for. So 1 over 2 minus x squared, and then I take the so that's the derivative, and I can multiply it into x cubed, and I get exactly what I'm looking for. Right? X cubed is just something I can multiply into the power series, and I do exactly that, and voila, there we go. So that's how you find the power series for this function. Okay, hope that was useful, or leave me some feedback if you want, or if there's something that's not clear, I can answer some comments or emails. Awesome, see you later.